Hello and welcome to today's lecture. Today we are going to discuss about microstrip antennas. So, in microstrip antenna we are going to discuss about different types of antennas, but we will start with a very simple thing, which is a rectangular microstrip antenna. Let us see what a rectangular microstrip antenna is first of all, and what is a microstrip antenna. So, a microstrip antenna is actually a very simple configuration, where what we have is we have a ground plane, and then we have a dielectric material whose dielectric constant is epsilon r, thickness of the substrate is h, and then there is a patch which is printed on the other side, and if the shape is rectangular, it is known as a rectangular microstrip antenna. If the shape is circular, it will be circular microstrip antenna, or if it is a triangular shape, it will be triangular microstrip antenna. And this whole thing is actually known as a substrate. It is very similar to, you might have seen a printed circuit board inside your mobile phone or TV or any electronic gadget. It is very similar to that we have a printed circuit board, where one side there is a ground plane or a copper, then we have a dielectric material, and on the top there is a copper. And in fact, if you see any of these microcontroller, they have so many parallel lines running here. But for a microstrip antenna, very simple thing which is required. Just keep the ground plane at the bottom as it is, so do not etch it out. So, that will be the case for majority of the microstrip antenna. And the top can be, as I said, it can be circular or triangular or hexagon shape, and that is what the name comes out from. So, let us just see the basic thing. We will start with the very simple rectangular microstrip antenna. So, a rectangular microstrip antenna is defined by its length, which actually determines the resonance frequency of the antenna. Then there is a width. In fact, we will see that if smaller is the width, lesser will be the radiation, larger is the width, larger will be radiation, which leads to larger bandwidth as well as larger gain. Now, we need to feed the antenna. So, we are using a coaxial feed to feed the antenna, and this coaxial feed is chosen such a way that wherever the input impedance is roughly 50 ohm, we connect with this 50 ohm coaxial connector. And in fact, the beauty of this is, so you can do the matching directly. There is no need of any external impedance matching network. So, let us just see what are the characteristics. So, we will compare here microstrip antenna with a microwave integrated circuit. The reason I am showing microwave integrated circuits have been in existence for very long time, whereas a microstrip antenna, the starting point was in 1953, where this was observed that there is some radiation going on, but it was almost 2 decades later, that was in 1974, when Munson had proposed how to practically use this one here. But again, MICs were there, people have been using MIC, and the substrates were getting printed. So, a substrate is defined by its different parameter, for example, dielectric constant epsilon r. So, for MIC we would prefer epsilon r to be large, whereas for microstrip antenna we prefer epsilon r to be small, and I will tell you the reason. And thickness, we generally take for MIC small thickness, for microstrip antenna it is large thickness. Width is generally taken small in case of MIC, we take large width in case of, let us say, rectangular microstrip antenna. Now, all these 3 conditions here actually lead to minimum radiation or maximum radiation. So, in case of MIC we do not want any radiation to take place. And how radiation takes place? It is basically from the fringing field. So, in the case of MIC we always want to minimize the fringing field, and in case of microstrip antenna we always want to try to maximize fringing field. So, how does this fringing field help? So, again think about that antenna which I mentioned to you, and on top of that we have a radiating patch. So, think about this, suppose if the patch is very thin. So, what will happen? The fringing field will be there, but that will be very small. Or before that, even think about a parallel plate capacitance. Suppose we have a one ground plane and there is another parallel plate. So, for the parallel plate there will be fringing fields all along, and if we increase the thickness there will be more fringing field. If the epsilon r is increased, which reduces the size of the antenna, then the fringing fields will reduce. So, the whole purpose for an antenna is try to increase the fringing field as much as possible. So, the main difference between MIC and MSA is that in MIC we do not want any radiation to take place. So, for example, the examples are filters, power dividers, couplers, amplifiers, etc. So, let us say if we are designing a low pass filter, what we really want is for lower frequency whatever is the input that goes as an output, and for higher frequency it should do the attenuation. But suppose if the radiation takes place, then what will happen? Let us say we are giving 1, we are not getting out as 1, we may be getting 0.9 or 0.95. Now, part of that can be accounted for, that there are some dielectric losses. So, that is why we need a good quality substrate, or there may be some conductor losses because of the conductor, but then there are radiation losses. So, MIC we want radiation losses to be small. For antennas we want radiation losses to be very high. In fact, the term radiation losses actually is used from circuit point of view, otherwise from antenna point of view radiation is the desired thing. Okay. So, now let us just look at what are the substrates to be used for microstrip antenna. So, we have given some popular names for the substrate. Let us say alumina is one of the substrate which was earlier used extensively and even today used extensively for microwave integrated circuit. Only in very few application we would use alumina for microstrip antenna, and most of the time that application could be a compact antenna. Now, the typical dielectric constant of that is 9.8, even though it may vary from 9.6 to about 10.2. It has a very low loss tangent which is 0.001. What is loss tangent? Well, it is related in the simpler way with dielectric constant. In a sense, a dielectric constant is a complex quantity. Epsilon r is actually defined as epsilon r dash minus j epsilon r double dash, and that can be written as in the form of tan delta, which is the ratio of the two epsilon r. So, it is very low. So, that means dielectric losses are very small. The only problem with the substrate is it is very high cost. Of course, alumina is not very useful as an antenna because it is a high epsilon r, leads to very less radiation. The next very low cost alternative is to use glass epoxy substrate, also popularly known as FR4 substrate. Now, this is the commonly used substrate for all printed circuit board. The typical dielectric constant can be 4.4, but in reality it may be from 3.8 to about 4.6. The problem with this is that loss tangent is very high, which is 0.02, but the big advantage is the cost is very low. I mean, just to tell you the idea between low and very high, the cost can be 30 to 50 times more than this particular substrate. So, overall cost of the antenna increases significantly. Now, these are the two popular brand names, Dioride and Arlon. Substrates are available. The typical substrate dielectric constant is around 2.2. In fact, this is actually a variation of glass. So, we know that glass has a refractive index of 1.5. So, refractive index is related to dielectric constant. Relation is dielectric constant square root of that epsilon r is equal to refractive index. So, if refractive index is 1.5, epsilon r will be 1.5 square, which is 2.25. So, these substrates actually are variation of this. So, in fact, they are typically fiber reinforced glass. Okay. So, fiber is put there. In fact, this is also glass, but epoxy is a lossy material, and we know that glass cannot be used, it can be broken very easily. So, that is why these fiber glasses are used, and typical dielectric constant may vary from 2.1 to about 2.5 also. I just want to tell you there is a Teflon can also be used. Teflon has a dielectric constant of 2.1. The beauty is that the tan delta is very small, it is 0.009, or it has a variation again 0.001 to about 0.0015 also, but again the cost is very high. We can use foam also. The foam has a typical dielectric constant of 1.05. you can see the loss tangent is really very small. The cost of the foam is in general very low, but if you want the graded foam, then that cost is about medium cost. And of course, the best material actually is air. Air has a dielectric constant of 1, loss tangent is actually 0, and you know that you do not have to pay for the air, right. So this is a really a good alternative, and in fact the lowest dielectric constant also leads to the highest bandwidth among all of these cases also, as well as the highest gain. The only thing is how to make antenna in air, and that is where lot of thought process has to go, how to use air effectively as a substrate. So we can see that this PCB is really a lightweight thing. I mean, you only need to do the print the antenna on a substrate. Now substrate is thin, so you can actually make out from there that it has a very lightweight, low volume, low profile, planar configuration, which can be made conformal. In fact, these days flexible PCBs are also available, which can be wrapped around the mobile phone, or it can be wrapped around the plane or missile or satellite and so on. So the fabrication cost is more, except that if you use expensive substrate, then the material cost may be more. But when we talking about a microwave antennas, the size is very small, so overall cost may not be too much. And since it uses the PCB technology, mass production is very easy. You can produce millions of pieces without any problem. Now using microstrip antenna, we can design it both for linear and or circular polarization. In fact, here also one can design antenna for both horizontal and vertical polarization. So that is very easy to do it. Now we can design very easily dual frequency antenna using microstrip. In fact, these days people have used tri-band, quad band, pentaband also using microstrip antenna. And another beauty is that feed line matching network can be easily integrated with the antenna structure. Now because of these advantages, it finds lot of application. Of course it has disadvantages. So let us see what are the disadvantages. So in the topmost, the disadvantage for microstrip antenna is the bandwidth is limited, which is 1 to 5%. Now I just want to tell you, my PhD thesis was on broadband microstrip antenna, and that was in 1979. I submitted the thesis in 1982. So it's almost like 34 years back. We had designed microstrip antenna for bandwidth of 20%, 25%, 30% also. So in these lectures we will talk about what are the broadband techniques, how to increase the bandwidth. Now the next disadvantage is low power handling capacity, which is obvious. If you use a printed circuit board which is very thin, how can you use it for high power? However, here also the remedy is there, that one can use metallic plate, thick metallic plate suspended over a air, and they can handle very high power also. The next practical limitation is on the gain. So typically microstrip antenna array can give us about 30 dB or so. However, nowadays lot of research is going on, so people have broken the barrier of 30 dB. So there are arrays of 32 dB, 34 dB, 36 dB and so on. But still, if somebody wants a gain of 40 dB or 50 dB, 60 dB or 70 dB, then the only solution right now is to use reflector antenna. Yes, there are some problems with the isolation between the feed and radiating element. So if you use feed to feed the radiating element, there will be some coupling, so isolation is poor. However, in the last 3 decades, lot of research has been done now how to increase the isolation. Excitation of surface wave. What is surface wave? So suppose, for example, if we take a typical microstrip antenna which is radiating, let us say in the broadside direction, which is perpendicular to the surface of the patch. But what happens, the fringing fields are there from the patch to the ground plane. So these fringing fields which are at the edge, they start propagating along the surface, and which is not a desired thing. Of course, again now lot of research is going on how to reduce the surface waves, and there are certain conditions If we meet, then surface waves can be reduced. Now, tolerance problem of low cost substrate is problematic. So, that is why we need to use good quality substrate which are expensive, but we will also show you how to use even a low cost thing for better performance. Polarization purity is difficult to achieve. Yes, it used to be a disadvantage, but nowadays again many techniques have come which improves the polarization purity. Now, of course, the one big disadvantage is that size of microstrip antenna is large at lower frequency. Now, so designing a microstrip antenna at, let us say, 1 megahertz is almost a forbidden thing, because at 1 megahertz wavelength will be 300 meter. So, even if somebody wants to design a lambda by 2 antenna which is 150 meter, you even make it on a dielectric thing, it is still running into 50 meter. Who is going to make a 50 meter printed circuit board? So, that is a major disadvantage. However, lot of research has been done to realize compact microstrip antenna, and I just want to mention, I had published a book on broadband microstrip antenna, and that was published by Artec House in 2003, and we have devoted one full chapter on compact microstrip antenna. So, as we can see that advantages of microstrip antennas are just too many, and even the disadvantages which I have mentioned, they have been overcome, many of them. So, that is why these microstrip antennas find lot of applications. So, if you look at your mobile phone, inside it has a microstrip antenna, or there is a variation of that, there are printed monopole antennas are there. So, pagers used to have microstrip antenna. So, Doppler radars and others, they use microstrip antenna. Satellites are major user of microstrip antenna because of its lightweight, low volume. Radio altimeter is typically used for an aeroplane. So, when the airplane is flying, it would like to know. So, microstrip antennas are fantastic because of its lightweight, low volume. It can be flushed with the body of the plane. These are being used in the missiles also. Again, the main advantage of all of these things is the small volume, and we can get all these polarizations and multi-band configuration. So, in fact, microstrip antennas have been used as feed elements in complex antennas also. In fact, more than a decade back, what we had done was we replaced the horn antenna of a 4 gigahertz parabolic dish. So, remember, decade back there used to be a large 8-foot parabolic dish which had a horn antenna as a feed. So, what we did, we studied the characteristic of the horn antenna which was feeding that reflector antenna, and that horn antenna was, we replaced that with the microstrip antenna, and we reduced the size significantly. So, when we are progressing in this particular lecture on microstrip antenna, we will show you the details of that. So, of course, it is being used for satellite, it is also being used for biomedical radiator. So, let us see what are the different shapes of microstrip antenna. I just mentioned about rectangular, but so many different shapes have been used. So, square microstrip antenna, circular, triangular. Even in triangular there are a lot of variations are there. Equilateral triangular antenna, isosceles triangular antenna, 30, 60, 90 triangular antenna, and so on. Then semicircular antenna, in fact people have used sectoral antenna also, 30 degree, 60 degree, 120 degree, and so on. Then annular ring can be used, or a square ring can be used, or even a triangular ring can be used. And besides that, there are many other configurations like the pentagon antenna, octagon, hexagon, and so on. So, depending upon the shape, and then lot of times you cut different kind of slits and slots, or use shorted configurations, and you can realize varieties of these different types of microstrip antenna, and one has to see what are the advantages and disadvantages of all of these configuration. So, how do we feed these microstrip antenna? So, there are various techniques how to feed microstrip antenna. So, one technique we have already discussed. So, here we have a rectangular patch, we are using a coaxial feed right over here. And what do? You take a coaxial wire you can connect that with the SMA connector or N-type connector, and what is normally done then, that coaxial wire or connector, the ground of that or the outer shield of that is soldered to the bottom ground substrate, and then the center pin is a drill hole is drilled here, that center pin goes through there and we solder it into the top patch over here, okay. And that's all a microstrip antenna is. So simple PCB, use a coaxial feed, it needs to be optimized, job is done. So that's a one type of the feed. Then say another type of the feed is a microstrip line feed, where we connect this microstrip line to the patch. In fact, this type of feed is very popular, especially for arrays where we have n number of elements and we need to connect all those n elements. So most of the time a microstrip line feed is used for that purpose. There are some variations are also there for this case. So one can feed, instead of feeding along this axis here, one can also feed along this. We will see what are the advantages and disadvantages, and instead of feeding here, one can actually feed it over here. This is also known as inset feed. Why it is done? In fact, this is actually done, if you recall, for coaxial feeds we were feeding somewhere here. Why we were feeding here? We could get the impedance matching. So instead of feeding here with the microstrip line, which impedance is high, as we will see shortly, so instead of feeding at this point where impedance is very high, which results in impedance mismatch, we actually cut a inset over here, reach to almost this point to get a matching. So that is what is known as a inset feed. And sometimes if we can't do any of these, what we do it is we use a lambda by 4 quarter wave transformer. So whatever is this impedance here, that can be transformed to the another impedance. So just to think about, if this impedance is say 200 ohm and what we really need is a 50 ohm here. So you can actually use a quarter wave transformer of 100 ohm. So input impedance at this is given by Z0 square by ZL, which is the load impedance. So if I take this as 100, so 100 square divided by 200 will give me 50 ohm impedance, which will be perfectly matched. The another way to feed is electromagnetically coupled feed. Actually speaking, there are two different substrates used here. So there is a bottom substrate here which consists of the feed line, and this bottom substrate can actually use the concept of MIC, that means high dielectric constant and thin substrate. So we can optimize the performance from MIC point of view, whereas the top substrate is printed on the, that is taken as a thick substrate of low dielectric constant, and then the patch is printed on that. And how this patch gets excited? This feed line is going there. So when this feed is fed there, we can see that the current will be 0 here, current will be maximum. So by using this electromagnetically coupled, so this coupling is through the magnetic field. So that magnetic field gets coupled to the top patch and it excites that. Okay, so that is what is known as electromagnetically coupled feed. Then there is another feed which is known as aperture coupled feed. So again it consists of the two substrate, one is the bottom here, another one is top here. This is the common ground plane, so it is just shown as a separate thing, you do not need separate. So this ground plane will correspond to this over here, so you just keep the copper as it is, but cut a slot in that here, and the patch is on top of the substrate, and on the other side, so this is on the bottom side now, there is a feed line. So again this feed line will actually have a current distribution which will have a magnetic field, that magnetic field will couple through here and excite the top patch. So that is how the top patch will be there. The only disadvantage with this particular feed is that there is a back radiation, so front to back ratio of this is relatively very poor. So now let us just look at a very simple rectangular microstrip antenna and how we define it. So this is substrate which has a finite size, and here is a rectangular patch which is shown over here. The feed is as before. Now we know that if there is a two parallel plates are there, there will be fringing field. So fringing field what does? It actually increases the effective capacitance. So for example, there is a plate capacitance that is given by Cp is equal to epsilon 0 epsilon r A by H, where A is area. Now there is a fringing field. So due to the fringing field, the total effective capacitance increases. So that can be compensated, that we just assume that the length is and width, they are arbitrarily more compared to the physical dimension. So if you look into that, then this is the fringing field around this. So what we have now, the effective length will be physical length plus delta L on both the side. Similarly, effective W will be physical W plus delta extension on both sides. And of course, to calculate delta L, there are so many numerous expressions are available, 1 line to 5 line and so on. But I suggest that you use this very simple expression, and that is delta L is equal to H by square root epsilon. And after that, what we need to know is that this length should be approximately lambda by 2 for fundamental mode. So the resonance frequency can be defined by this particular expression here, but just to make things simple, majority of the time we use a fundamental mode which is 1 0. So this is 1, this is 0. So if this is 0, this term is out. This is 1 here, so 1 by L square root, it comes out here. So frankly speaking, F0 is nothing but C divided by 2L square root epsilon. So I just want to share, so L is nothing but equal to lambda 0 by 2 and Y square root epsilon, because that is the effective wavelength. And we substitute lambda 0 equal to C by F. So just by using this simple expression, we can find out what is the effective length. So in the next lecture, we will talk about how to design rectangular microstrip antenna in less than 15 minutes, and maximum error it will be just about 1% or so. So in the next lecture, we will see how to design rectangular microstrip antenna. We will also see how to choose a proper substrate to get the desired bandwidth, and then we will move on to the other geometries like circular microstrip antenna, triangular microstrip antenna. We will also cover how to increase the bandwidth. So what are the different broadband techniques are there. We will also see later on how to realize a compact antenna, how to design circularly polarized antenna, and then towards the end we will talk about lots of different microstrip antenna arrays which can realize different desired gain as well as half power beamwidth. So thank you very much. Looking forward to see you next time. Bye.